Hi there, and welcome to this breakout session on SolidWorks Simulation, where we're going to be having a look at stress and also fatigue failure mechanisms and how we can use SolidWorks to analyse those before we go ahead and produce our designs. So what we're going to be doing is having a look at a basic bike crankset design. We've got three potential designs, and what we're going to do is analyse those individually to see which one's going to be best before we go ahead and actually produce anything physical. Now, fatigue failure is a failure mechanism which is well appreciated within the engineering industry, and it's something that occurs within designs that are loaded repeatedly in a cyclic fashion. So when we look at our design, we can see that despite the fact that we're not applying stress or loads that will incur stress higher than the yield strength of our material, we may still see after a number of loads that material strength reduce, and hence a failure as a result of numerous cycles at a stress that was significantly lower than that of the yield strength of the material. So as I said, what we've got here is three main designs. Hopefully you'll be able to see the difference between the three that I've got on my screen now. And we've got a very specific setup criteria that we're going to have a look at in this case. So you can see we've got fixtures where each of these bolt holes is, around here, and as highlighted by the blue pedal, we're going to apply about 21 stone force downwards, normal to the top of that pedal. And what we're looking at in this case is a minimum number of cycles of 7 million. So if any of our designs don't meet that particular criteria, we're going to deem them all as failures. Okay, so having a look at our model now, you can see that I've already gone ahead and created an alternate configuration, which is what I'm going to use for my analysis. So that sprocket that we had on there is the first thing that you'll see will have disappeared, and that is unnecessary detail. We're not going to analyse that because we're fixing at these 5 points, and we're assuming that the stress is going to be somewhere in the crank arm. That's the bit that we're concentrating on. Okay, so let's go ahead and set up a new study. Now this is very easy. SolidWorks has put in a lot of effort and a lot of time into integrating the simulation tools into your standard SolidWorks environment. So over here you'll see I've got a simulation tab, and you'll see that I can go ahead and create a new study just like that. I can give it a name, so here I'm just going to call this FEA test, for example, and hit OK, and you'll see SolidWorks is going to give me an FEA test tab at the bottom and still allow me to switch back to my model if I want. So that's a very nice feature that SolidWorks have added, giving this the opportunity to switch in and out of our study with relative ease, which is something that you won't get in a lot of other packages where perhaps you might have to export your study, so export your geometry into the full design environment, and then once that's done, you have to, if you want to make a change, you make the change to your geometry in SolidWorks and export it again and reset up the study. This is very simple because all of the selections are based on the internal IDs of the faces and the geometry that you've got on your screen, so when you make a slight change, SolidWorks remembers everything else and will keep it all set up for you. So first of all, you'll notice in our tree on the left hand side we've got a list of all of our parts. So I'm just going to right click on here and apply material to all. And so you'll see that in here, SolidWorks has given us a very vast database of potential materials that we may wish to use on our design. So we've got steels, we've got irons, we've got aluminium alloys, etc., etc. The list goes on. So in this case, you'll see that I've already been ahead and applied materials to each of the individual components. But in actual fact, what I'm going to do is make a change to these. Now I've already got a previous study set up, and you'll see that I've chosen a couple of different materials for each of these components. So I want to use those same setups in my current study. Now without going through and changing each of the individual materials for each of the components, I can instead select each of these. I'm doing this just by holding down the control button, drag them and drop them onto my new study, and you'll see that now the same materials have carried across into my current study. Again, SolidWorks putting a lot of time and effort into making sure that the user environment is very friendly to the designer instead of having to be an analysis specialist to use the tool. Okay, next I'm going to set up what are referred to as contacts. So this is the way in which each of the individual components that we've got in our study will interact with one another. So let me just go ahead, grab my contact set, And you'll see that SolidWorks makes it possible, so I'm going to set this up as a bonded contact, so I'm going to stick them together. And SolidWorks makes it possible for us to just select geometry from the screen, like so, and that's it. You see our bonded contact has been added in here. Very simple, we're just picking off the geometry that we've already been and created in SolidWorks. Next we're going to go ahead and apply some fixtures. So you see at the right click of my mouse on the fixtures icon, we get a list of all the potential fixtures that we can apply. In this case I'm going to use a fixed hinge, so I'm going to grab that guy there, and you'll see the fixed hinge window comes up. As we go through each of the individual fixture types, you'll see that as we click the icon, we do get a nice little animation that's SolidWorks' way of showing us what it is that we're going to apply to our geometry. In this case, I'm going to grab that fixed hinge, and you'll see we get a nice visual representation of what's going on. And so that allows us to grab the faces that we're interested in. I'm just going to pin this in to keep the tool open when I hit OK. And you'll see we can add that fixture on there. So I've got the green arrow signifying that fixture that I've placed. I'm going to do something similar for all of these bolt holes. So this fixture is just going to constrain any radial and axial movement, but we're still allowed to move in the circumferential direction. So potentially we're allowed to rotate about each of these cylindrical selections, but obviously because we've got 5 spread out, that's going to constrain the movement entirely. Okay, that's me done, and so you'll see we've got our 2 fixed hinges in there. The next thing for me to do is apply our loads. So as you recall, I'm going to apply that to our pedal. So first thing I'm going to do is right click on my external loads and come in and generate a force. So you'll see again we've got a list of all the available things that we can apply to our geometry. In this case I'm just going to use a force. And I'm going to select these top 2 faces here. Next I'm going to specify a direction, so SolidWorks allows me to control the direction of that force application just by using simple reference geometry. So in this case I'm going to grab my front plane and I'm going to ask SolidWorks to place that force in the normal direction to that plane. So as I put my 1335 newtons in here, again that's about 21 stone, and you'll see SolidWorks has stuck in arrows on the screen which are depicting where the force is acting. So in this case you'll see we've grabbed the right face, but the arrows are acting upwards, which isn't exactly what we want. We've got a reverse direction button down here, just hit that and SolidWorks is going to flip those arrows so that we're acting in the correct direction. I hit OK, and that just adds that item to the tree. We can edit these very much like standard SolidWorks features in the design interface just by right clicking and going to edit definition. Now for those of you that are unfamiliar with FEA, one of the key things that dictates how accurate our study is going to be is the mesh. Now this is how we're breaking our model down into a number of finite elements, hence the name finite element analysis, and the finer the number of elements, or the smaller those elements, so the higher the number, the more accurate our results are going to be. But the more time it's going to take because the more elements SolidWorks has to resolve. So it's up to the engineer to try and resolve that. But what we can do is control our mesh by using a number of different features. So first of all I'm just going to come in and apply a standard mesh like so, and you'll see SolidWorks will whip through and automatically generate that mesh for us based on what I've left at default settings for the time being. Then SolidWorks, as you can see, is going to display that on the screen for us to review. So we can see I'm happy with most of it. Perhaps we've got a lot of curvature in here, I might want to change that a little bit. And the pedal I'm not so concerned in, so I'm going to make sure that we've got a nice coarse mesh on that pedal. So I'm going to right click on my mesh and come in and create what are called mesh controls. And this allows me to just simply grab items, so in this case I'm going to grab my pedal, change the mesh density, hit OK, and SolidWorks will add that item to the tree. I'm going to do a similar thing over here now for some of these curvature regions. So I'm going to select some faces this time. I'm going to do a little bit over here as well, perhaps those guys there and those guys there, something like that. And in this time I'm going to put a numerical value so I can be as specific as I like here. So I'm going to put 0.889 millimeters in there, so you can see we can be as precise as we wish. And then when I come back and ask SolidWorks to mesh that again, pay attention to this region here. SolidWorks is going to take that information that I've put in into account and update the mesh accordingly. Okay, so you can see we've got a significantly finer mesh in these regions now, which is going to allow us to better capture what's going on in those areas of high curvature. So finally, I'm just going to hit run, and you'll see how quickly SolidWorks is going to whip through that and solve that for us. And you see, as it goes through, we do get a nice heads-up display of what's going on, so we can see what sort of stage it's at in the solve process. So the final part, that stress calculation, then SolidWorks will output the results for us on the screen. And there we go. That is the typical default output of the stress results. So we've got a color contour plot depicting the high and low stress regions within our geometry. I'm just going to grab those glasses and turn the icons off because they can get in the way sometimes. So once we are done setting the study up, we don't necessarily have to have them on the screen. And now we're going to have a quick look at some of the results tools. So first of all, obviously we've got our output color contour plot, but we can get a lot more information out of that. We can really delve into the numerical results, which is something that you can't quite do with such effect with a physical test. So once you've loaded this and it's broken, that's it. You've got a broken geometry, and you can see where it's broken, and perhaps from the pattern on the surface of the break, you can see what type of failure it was, but that's about as much information as you get. Whereas here we can really analyze the numbers and have a look at exactly what's going on, where and why. So first of all, I'm going to right click on my stress plot. I'm going to animate it. So this is just a nice output that you can send to customers, or it's a nice easy way to show to other engineers, etc., what is going on as you load up this particular design. And then I'm going to come in and take advantage of the next tool, which is called section clipping. Now what SolidWorks have done is given us the opportunity to drag a plane, essentially, or we can use a cylinder or a sphere through our geometry, so we can have a look at what's going on inside the walls. So we might be able to see very nicely what's going on the outside, but that's not always of concern, but perhaps sometimes you might want to see what's going on inside. So if I hit OK here, you can see we can zoom in now and have a look at exactly what's going on inside the geometry, which is absolutely lovely. I'm just going to turn that back off now. And we'll have a look at probably my favorite, and that's the ISO clipping. Now the ISO clipping is a tool that allows us to isolate bands or areas of stress. So via this arrow we can choose to display either the stress values above what we're specifying or the stress values below. In this case we're looking at above. If I flip that, you'll see that we get what's below. Let's go back to the above. And what we can do, and this is really nice, is you can drag this slider down through the higher stress regions and see where that stress is beginning to pick up. So we can see we've got 4 sort of key points or key regions of stress coming in. We've also got a couple of extra points coming in here which we might want to keep an eye on. As we bring that through, we can see how that stress propagates throughout the rest of the geometry. And it's actually a nice neat way of analyzing how the stress is being, or the load is being transported from our load location to the fixtures. So we can see that the bulk of the stress is being taken by this particular region here in the middle of the crank arm, and also at the root just here and here. As we bring that down, we can see that we've got a nice complete line now from the pedal through the crank arm and straight to these first few fixtures. You see the fixture over here isn't going to be providing as much support in this particular load case as the other two that we've got over here. We might be able to streamline or lighten the way in which we produce this side. Okay, next we've got one final tool which is referred to as the probe tool. Now the probe tool is a more numerical way of getting results out. So far we've seen very visual results. They're all very clear but colourful and not particularly precise results. Instead what we can do is grab that probe tool, come in here, and for example if I just grab a couple of locations around here, draw a line with some points essentially, like so, you'll see SolidWorks is populating this table on the left hand side with each of the nodes as I've selected them. So it's picking the nearest node to where I've clicked, and it's outputting the stress value at that location and also the position of that location. We can also see the sum, a couple of numerical, essentially statistical outputs of those values, and nicely we can plot a little graph which is outputting the variation of the stress as we go through those selections. So this is in the order that I've selected them in this case. Okay, we can instead, if we wish, grab, for example, just a line there and plot on selected entities. So if I update that, SolidWorks will grab all of the nodes that make up that line, and we can do something very similar. So here we can see how the stress is varying along the length of that line. Now, one thing actually I will draw your attention to is, if I switch over to my displacement plot, you'll see that it does look significantly bent. Our geometry does look like it's not performing particularly well at all. It's twisted and it's bent downwards, and we've got, despite the fact that we've got very small displacement, it looks like we've got a lot. And that's because we've got this deformation scale on here. It's been exaggerated for our eye. So we can turn off that deformed result, and that's just going to paint the results onto the original geometry. Or alternatively, we can just edit the plot and make it a true scale. And that's going to output the geometry at its actual physical state after we've loaded it. So this is how the geometry would look in real life. Alright, and that's about all there is to setting up a study using the linear static stress analysis tools. We've also got the capability to analyze fatigue. So this is an add-in, so that was functionality that's available to us in SolidWorks Premium, but there is an add-in that's available to us with SolidWorks Simulation Professional, which allows us to analyze fatigue. So I'm going to set up a new study now. I'm going to grab a fatigue study and hit OK. And you'll see now we've got an additional study at the bottom. I didn't give it a name this time, I've been lazy and called it Study 1. And in this case we've got a much, much smaller tree. I'm just going to right click on the loading here and go to add an event. As we specified earlier, I'm going to stick 7 million cycles in here. So that's 3 zeros, another 3 zeros. And we can choose which study we wish to use. So we've already set up an FEA test study, and that's the exact load that we want to incur just on a repeated cycle. So I'm going to select that, and you can see we can choose that cycle in a number of different modes. In this case, we're going to use a zero-based, so essentially the load is going to be applied and released over and over and over again. We could fully reverse it, so we could apply it, release it, apply it in the negative direction, release it, apply it, so we get a full wave. Or we can also use some additional options for combining numerous studies. So if we've got more than one stress analysis study, we can find the cycle peaks, which is going to be the worst case scenarios based on all of those individual studies. In this case, we're just going to use the zero-based. Hit OK. And that is pretty much it. We've already got our components already brought in. All I'm going to do is quickly pop this up and show you how we can add in our SN curve. So our SN curve is the variation of the number of cycles to failure with respect to the load that we're putting on, or the stress that we're putting on. So we can stick this in here. So here you see we've got a number of values, and we've got our SN curve just there. Now SolidWorks is just going to use the basic miners law, which is a very well understood and accepted principle for analysing fatigue. Obviously it's not exact because surface finishes and anything, any slight imperfections can have an impact on that, but the miners law is probably the most well accepted approach for analysing fatigue. So I'm just going to hit run, and hopefully you'll be impressed by how quickly this runs. So once the box comes up, you'll see there really isn't much to it. Once we've already conducted that FEA test study, SolidWorks is just dealing with the numbers that it's already got, applying a small numerical calculation, and you'll see how very quickly that has solved for us. So if I expand the results options now, we can have a look at the two options we've got here, or alternatively we can apply a new one if we wanted. And so, for example, here in this case, after 7 million cycles, we can have a look at the damage that we've got there. So our damage percentile value is currently sitting at 475, which is essentially a failure. So after 7 million cycles, we have long surpassed failure. And in this case, you can see highlighted there where our highest damage is and where hence our lowest life is. If I switch over to the life, we can see a plot which is just essentially showing us what the maximum and minimum life is. So in this case, our minimum life is 1.4 million cycles, and so that is mostly in this on the entire crank, but you can see we've got a big dark blue region around here and around on the top section as well, and probably around in these parts as well, where we've got that higher stress. So we can see our maximum number of cycles here, about 1.5 million, is nowhere near. Alright, so going through each of our individual studies, we can see, so I think I might have changed the setup on the on design 1 to a previous time, but we can see that we can very quickly analyze each of our individual designs for the number of cycles. We can see what the maximum stress is, we can check what our factor of safety is, and so here you can see, comparing the three designs, we started off with a very low number of cycles, about 1.5 million. Obviously, again, it's very much a ballpark figure, but we can see roughly where we are. And you can see that our weight came in at 392 grams. Now I've added some material here, which is going to strengthen, in certain locations, which should strengthen the geometry, and it has in this case. So those 12 grams of material that I've added in, wherever it's been added, has improved the number of cycles to failure by no end. So here we can see our max stress has been reduced to 196 megapascals, and now we're at almost 20 million cycles before failure. So that's a significant increase in performance. Now I've gone another step and actually applied further materials. So here again we've put another 16 grams on this time in some additional locations. And what this has actually done is generated some stress concentrations and weakened the geometry. So in this case we've stiffened parts that didn't need to be stiffened, and that's transferred the load onto parts that are weaker. And now we've got a maximum number of cycles, about 500,000, so we've really damaged the performance of our geometry there. So here we can see that adding material isn't always the best option, and we've used SolidWorks to analyze that and optimize our design. So just to reiterate, we've been through and achieved a more reliable design. We haven't spent a penny yet, and I would have thought setting that up and analyzing all three of those individual studies that we had there would have probably taken me about half an hour to 45 minutes if I was doing them all in one go. And to reiterate, we haven't spent a penny, we haven't made anything. We can do that now, but we've already achieved an optimum design, and we can push forward with that one design instead of having to analyze three at a time when we go through to our prototyping phase. Alright, thank you for joining me, and there will be another breakout session on flow simulation, so please do stick around and have a look at that as well.